Welcome back, folks. I hope you're going to enjoy this one. We're going to be looking at Venn diagrams, and with Venn diagrams, we are literally going to want to stick to the aspect where it concerns our gates. This is where we are going to understand the mean term and the max terms. All right, now let's go and see what are Venn diagrams. We would normally talk of a universal set. Let's draw in a universal set. Universal set, as the word universal suggests, it is everything. It is everything. If suppose I said, what do you call this? A simple example. Let's say animals. All right, all animals. That's a set. I could make a set out of that. Then, why we call it universal? This will include everything that qualifies as an animal. All right, we normally refer to this as the. Oh, I've got a rubber there. Instead of a pen, we will have our universal set. All right, but within there we will have different types of animals. Some of them will intersect with each other. All right, others will be independent of each other. All right, this is if I have a scenario. Let me try and treat different scenarios. Let me say, let's start with a set. Let's say we have a set. If this is a universal set of animals, for example, then let's say I go and say I want to see a set of domestic animals. Let's call it A. We call this domestic animals. All right. It's not every animal that is what? That is a domestic animal. It's not every animal that you can domesticate. You've got your dogs, you've got your all your pets, your cats and whatever, your horses, your donkeys and all that, your cows. This will belong to a set of what? Of specific animals that we call domestic animals. But you can't have a lion in this set, all right? You can't have a buffalo in this set. You can't have a zebra in this set because they are not domestic animals. So now, what you need to understand here is that this set here, if we are now going to talk of set A, we are going to find within that set, with the example that I'm using here, you are going to find domestic animals. Now, what are the other animals that are not domestic with reference to A? This will be called the complement of set A. What we call A's complement. All right. A's complement, also written as A's complement. All right. This here means not A. This basically means not A. All right, that means it does not belong to A. What does this mean? It means all animals, the universal set, minus A. All right, it's all the animals that are outside of A. If I'm to shed this, all right, let's go back and say we wanted to know what A was. I would shed A and say this is set A. The shaded area there represents set A. All right. Now, so A is the shaded area now. If I want the complement of A, it means everything that is outside of A. So the complement of A would therefore be, if I'm to shade the complement of A, I would have to shade everything that is outside of A. Universal set minus A, everything outside A. Okay, if I'm to represent not A or the complement of A, we would have, already I'm speaking get language. I'm already saying not A. All right, so this would be our not A. So this represents A's complement. All right, initially when I think I slipped up, I did not shed A, what call this A when we're speaking about A. I think going forward I'll be shedding. Each time I refer to something, I'll be shedding it. So what do you understand here? We've looked at A, all right, and this was within A. Now we're looking at the complement of A, which means everything outside of A, all right. So now we then say, okay, fine. Let's see, domestic animals. If I'm going to have, let me treat a different scenario. So what do we have now? We have said we have a set A. We've said we have a set not A, all right. So what are we seeing there? We are seeing that our first gate there, the NOT gate, has literally been the complement. All right, the complement of a specific set. Complement. All right. So now we go on and say, if we were having a, let's go on to the next option there and look at other possibilities here. I want to make sure I cover everything. All right, that one was escaped there. Let's go and say, what if we have two sets that are independent of each other? Let's have two sets that have absolutely nothing to do with each other. Okay, these will be referred to, let's call this set A, set B. These sets will be referred to as what? These sets will be referred to independent sets. A is independent of B. This will be independent sets, meaning there's nothing at all that is common between them. All right. Now let's suppose we talked of birds versus animals. All right. Let's suppose our universal set was something else, and then you say creatures. Let's say it was a set of creatures or whatever, and then you say we have birds, and then we have animals. All right. Well, someone would argue and say maybe the bird would qualify in both. Is the bird really a bird? A bird is not a bird. A bird is an animal. Ne? It is an animal that flies. We didn't say animals that fly. We said birds versus animals. So there is nothing that really links the two. I wonder if someone would say some birds qualify as animals. I wonder. I wouldn't think of it like that. So I'll say if, okay, let's think of anything else. Let's say solids and liquids. Then let's talk about something else. Then let's say matter. Let's say our set here was, our universal set here was matter. All right, and then solids and liquids, they are totally independent of each other. Even though someone would say, all right, what if I melt a solid? It then becomes a liquid. But we are talking about solids. When you've melted it, it's no longer a solid. Ne? It is now liquid. So it will be totally different state. All right. So when you're talking of sets that are independent of each other, we call them independent sets. Or, I think the best way is to say, to call them independent sets. All right. But there are sets that really have some things in common. Let's take... let's move this set closer and put it in there. All right. So let's suppose now you had animals. We'll go back to our universal set of animals and say, okay, one set of animals is what? Is two-legged animals. All right. And then the other set is what? Is four-legged animals. All right. Now, no. Let's say I've got a set of domestic animals. All right. And then I've got a set of four-legged animals, four animals with four legs. Ne? Now, what then happens is, do you have domestic animals that have two legs? Do we? I can only think of apes. I can't think of a domestic animal that has two legs now, can I? Okay, maybe let me change my set to four-legged animals versus domestic animals. All right, let's rather do that. Let's rather have A being a set of what? Of four-legged animals versus domestic animals. We know that we have, in this case here, do we have four-legged animals that are not domestic? Yes. Do we have domestic animals that are not that don't have four legs? No. So then B would not exist in this scenario. Probably have a wrong set here. Let's rather say B would not exist in this scenario. Let me rather make A little bit bigger. Let me make A little bit bigger. Let's have our A right there being a much larger set. I'm gonna make it funny because I want to keep drawing this. And then let's make B a set within a set. All right. Now, if you look at A, B, all members of B are actually an element of what? Of A. Are actually elements of what? Of A. All elements of B are actually elements of A. This will be called a subset. In this case here, B is called a subset of A. B subset A. That's how we write it. That little thing there means subset. B subset A means all elements of B are found in what? In A. So this is where you have your domestic animals, all of them having 4 legs that I can think of. I can't think of those that don't have 2 legs. Okay. And then you say how many of them are what? How many of them are domestic? All of them that are domestic have 4 legs, like I said. And then, but you have other animals that are what? That have 4 legs but do not have, that walk on 4 legs but do not are not necessarily domestic. So let's take your lions here, okay? Let's take your zebras there, let's take whatever. But this one here is all your cows, your goats, and your sheep and whatever. They are a set within a set. We call that subsets. Okay, this is a subset. Okay, subsets. All right, it's sets within sets. All right. However, I'll go back to my initial story there where I wanted to have intersections, right? Where we have a set and another set. Let's think of numbers. Let's say we have a set of even numbers. Let's say B is a set of even numbers. All right. Let's say even numbers. All right. Let's say the universal set is numbers from 1 to 50. Okay. Let's say here we've got a set, what call this? Multiples of 5. Multiples of 5. How do I do that? Let me just say times 5. All right. Let's say here, this one is what? A multiples of 5. I'll just say times 5. A is multiples of 5. All right. I'll just use times 5 to represent that. Now, we do know that from 1 to 15, we have got the number 1. It's not even. We've got the number 2. It is even, but it is not a multiple of 5. We've got the number, what am I doing there? 1. I've got 2. I've got 3. It is not even. It is not a multiple of 5. I've got 4. It's even. I've got 5. It's a multiple of 5, but it's not even. I've got 6. It's even. Let me not make a range. I'll never finish. Let me make a range up to 25. I'll never finish here. All right. It will take us forever. All right. Let's go to 7. 7 is neither a multiple of 5 and it is not even. Let's go to 8. 8 is even and it's not a multiple of 5. Let's go to 9. It's not. It's neither. Let's go to 10. However, 10 is both a multiple of 5 and it is an even number. Let's go to 11. It is neither. Let's go to 12. It is even. Let's go to 13. Let's go to 14. Let's go to 15. 15 is a multiple of 5, but it is not even. Let's go to 16. It's an even number. Let's go to 17. It is neither. Let's go to 18. It's an even number. Let's go to 19. It's neither. Let's go to 20. 20 is both a multiple of 5 and it is an even number. So let's go to 21. It is neither. Let's go to 22. It is an even number. Let's go to 23. It is neither. Let's go to 24. It is even. And of course, we have 25, which is not even, but it is a multiple of 5. So now when you say, what are the elements of set A? Let's say A elements of set A is going to be 5, 10, 15, 20, and 25. So these are what are elements of set A. All right. So now it's all the what? It's all the numbers that are what? That are multiples of 5. Let's go to set B. B is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. Those are all, that is a set. Set B is a what? Is, what call this? A set of even numbers between 1 and 25, inclusive. All right. Now, what are the other ones? We've got 1, 3, 1, 3, 7, 9, 11, 13, 17, 23, 20, 19, 21. And all these are what? Are elements that don't belong to what? To either A or B. Part of the universal set, but they don't belong to either A or B. Now, when we talk of what call this? When we talk of intersection. The intersection is where both A and B are satisfied. So A and B already spells out to you an AND gate. So this is what? This is, if I'm going to represent the AND, it is therefore the intersection A intersection B. This is A and is equal to, with the given situation that we have there, A, symbol for intersection is this, A intersection B. This is what? The numbers that are found in that shaded space there. All right, this is A intersection B. That is our AND. All right, so let's go then now and say what we call the numbers that belong to both sets A and B. It is called the, if I unite A and B, all the elements that are found in A and B combined. Remember, even if sets are independent of each other, all right, we still have A and B being everything, as long as they are what? As long as it's A and B, the union, which is called the what? The union, A union B. It means every element that is found in what? In either set. All right, so it is all of them combined. Now in this case here, our A union B, it's not a really U like that, it's a U without the little tail. Let me rather, the union symbol is a U without a tail. All right, that is going to be equal to, if I draw it, it's going to be, if we have an intersection, this is going to be, so what are the elements? What elements do I find in A union B? It is whatever I find in A or B. A or B. Therefore, this is our OR gate. Okay, this is everything that I find in what? In A or, what I do here? I said I said AND. This was a major flop here. What I find in both A and B, so it's actually A or B. I don't know what made me write an AND. We already dealt with the AND there. The AND is actually here. All right. Here is where you find things in both sets. Where you find things in both sets. But when you want the total occupants of both sets, that is called A or B, or the union of what? Of A and B. For independent sets, you would have it like that, all right? But for sets that intersect, it is still everything found in both of them. This is A or B. So our union actually represents A or B is actually the union of A and B. All right. So now we have other terms that we use here. For instance, okay, I already mentioned the complement. You know, it is everything. If I look at the complement, let's go to A. The complement of A, also written, remember, or A complement or A not. All right, the not get. All right, the complement. It is, if I'm to use this set here, A complement is everything that is found outside of A. Everything found outside of A. Not in B only, in the entire universal space, everything outside of A. Remember when we shared it, if we shared not A, or the complement of A, we will shed everything that is found outside of what we won't shed is the A itself. All right, so this will be everything found outside of A. All right, this is the complement of A. Likewise, the complement of B is everything that is found outside of B. So here it will include every number except 5, 10, 15, 20, and 25. It will be every number except 5, 10, 15, 20, and 25. So the union of A, the union in A and B, A union B would have been everything found in both A or B. If I find it here, it is part of the union. If I find it in either set, that will be the union. All right, but do not confuse matters. I was explaining now the what? I was explaining now the. Oh, how did it include? How did it include my set? I'm not gonna go at this one by one now, am I? It's gonna take forever. Okay, probably. Let me employ a little trick. As long as hopefully I will not accidentally remove any of my elements. Okay, so how did that group with that one? Are they grouped now? Let's see. Why is it going with it? Anyway, but it's fine. So if I'm going to use the complement of what? Of B, it is also everything outside the set B, which means the 1, the 3, the 7, everything that is outside the 1, 3, 7, 9, 11, 13, 17, 23, 19, 21, including 5, 15, and 25, because they are outside of B. The complement of B is everything that is external to B. All right. So understanding the complement, understanding the what? The universal set. Can we have a complement of a union? Yes, we can say. What about A union B complement? Okay, then that will be everything outside A or B. All right, everything outside of the collective of A and B. All right. So I'm trying to bring in. Okay, there's a whole. I want to actually deal with Venn diagrams with relation to what? I'm just giving background here. I want to deal with them in relation to our gates. But there's if you want to learn more on what? On Venn diagrams, I think there's a session on the mathematical, when we're doing maths, where we'll specifically look at each and every one of those Venn diagrams in greater detail. All right. But for now, I hope that gave us background, because I want to deal with two specific cases. All right. Which is these two cases here. If you are to look at A or B versus A and B, you can see that if you look here, this is the maximum of A and B. This is the maximum of A and B. Hence, all terms are called max terms. Max terms. Now, what am I doing? I want to max terms. They are terms of the maximum set, because as you can see, it includes everything. It is the biggest possible scenario of between A and B. All right, this is the biggest set. All right, between A and B. That's why we call it max terms. The sum terms are called the max terms. The odd terms are referred to as max terms. Hence, when we do our what? When we do our Boolean algebra, we call the product of sums also the product of max terms. All right, it is because that's why we call it the product of max terms, capital to say max terms. All right, and when you look at this is the least possible group. If there was nothing there, this is the least, the minimum, the bare minimum of the entire set. This is the bare minimum of the entire set. The smaller the relation between A and B, the smaller that set even becomes. Right? This is the bare minimum of the what? Of the relationship between what? Between A and B. Hence, we call the end. The end, we refer to it as a mean term. So now we've got min terms and max terms. And what does it mean? That's why we call the product of sums, because the sum of products, that's why we call the sum of min terms. Why? Now the Venn diagram makes this very clear. All right, I hope you understood that the whole concept, this whole thing was giving background in case some people don't have a sound background on what on I believe it was a crash course in Venn diagrams, but this was basically to give a background as to why we refer to our products as Minterms and our sums as as Maxterms. So I hope this was clear. I hope in future the confusion has been solved and we are now happy to proceed with our Boolean algebra. We were doing Venn diagrams here as a small feature of as a small aspect of our Boolean algebra. Thank you so much for being with us. Hope you enjoyed, and please stay and come back again. We'll appreciate that. Ciao.